look around you for a second. Seriously, if you're in your car, glance at the dashboard. If you're holding your phone, which let's be honest, you probably are, look at the casing. We live in a world just built out of these plastic parts. Millions and millions of them. And here's the thing we never really think about. They are all identical.
It is pretty staggering when you stop and think about it. The scale of it. We just take for granted that these things appear on shelves, as if by magic.
Right.
But someone had to figure out how to make 1 million of those phone cases without going completely bankrupt on waste.
Exactly. And that is what we are digging into today. We're looking at a technology that, okay, it sounds incredibly technical, hot runner injection molding, but it's actually a fascinating study in efficiency, physics, and some pretty high-stakes economics.
It really is. It's all about engineering a system to keep plastic alive, basically, molten, inside a giant block of steel so you can manufacture at speeds that just seem impossible.
I love that phrase, keeping the plastic alive. To help us get our heads around this, we're looking at a really comprehensive technical guide from First Mold.
Oh yeah, they do great work.
And specifically an article by their expert James Lai. It covers the process, the engineering, and the pretty serious cost implications of getting this right. Or wrong.
And Lai goes deep. What's great about this source is that he doesn't just sell you on the benefits. He's very clear about the risks. Because this is not just a push a button, get a part kind of deal.
No.
It's a complex thermal balancing act.
So our mission today is to unpack all of this. We're going to figure out how it works, why it totally changed the manufacturing game, and why, for all its efficiency, it can be a complete nightmare if the engineering is off.
Let's do it.
Okay, so before we can appreciate the hot runner, we kind of have to understand the old way, right? The source calls this the cold runner system.
Right.
I think most of us have a vague idea of injection molding, squirt hot plastic into a mold, but can you walk us through the traditional method?
Yeah, of course. So in a traditional system, you have your mold, which is basically a negative of the part you want. Let's say a bottle cap.
Okay.
The machine melts plastic pellets into this goo. You then shoot that goo into the mold. But the plastic doesn't just sort of teleport into the bottle cap shape. It has to travel down a channel.
A runner.
Exactly, a runner. It gets the plastic to the actual part cavity.
So it's like a hallway leading to a room?
That's the perfect analogy. The plastic fills the room, your part, and it also fills the hallway, the runner. Then the whole mold cools down to solidify the plastic. But here's the problem with a cold runner.
The hallway freezes too.
The hallway freezes too. The plastic in the runner solidifies right along with the part.
So for every single part you make, you're also making this useless plastic stick that you don't need.
Precisely. That's the runner waste. You open the mold, the part falls out, and this solidified runner, this little plastic skeleton, falls out attached to it.
And you have to cut it off.
You have to cut it off. You either throw it away, which is terrible, or you have to grind it up into what's called regrind and try to recycle it. It's just inherently inefficient.
It sounds like cooking a meal where you have to throw out the pot and pan every time you serve a plate.
That's a great way to put it, yeah. And that's where the hot runner system comes in. The whole concept, as Little explains it, is that you keep that runner system molten. You never let the plastic in the hallway freeze.
So kind of like my home plumbing, when I turn on the tap, water comes out right away because it's sitting in the pipes, liquid and ready. It doesn't freeze between uses.
That is it, exactly. The pipes in a hot runner system are heated. You have a component called a manifold, which is the main distribution block, and then nozzles. And these have their own internal heaters, their own thermostats.
Okay.
So plastic gets melted, moves into this hot manifold, spreads into the nozzles, and just waits right there at the gate.
And the source mentions these gates, like talks about thermal gates versus valve gates. What's the difference there?
Well, think of the gate as the door at the very end of the hallway. A thermal gate is passive. It just uses the mold's cooling to freeze a tiny plug of plastic at the tip so it doesn't drool.
Okay, so it just solidifies right at the entrance.
Right. But a valve gate, and this is the high-end stuff, has a mechanical pin that physically moves forward and closes the opening.
Like turning off a faucet.
Exactly like a faucet. You get incredible control. But the main takeaway is, when the part ejects, the runner plastic stays hot. It's ready for the next shot instantly. No solid waste.
Which brings us to the big why. I mean, why would manufacturers spend all this extra money? I can't imagine keeping a block of steel at 400 degrees is cheap.
Oh, it's definitely not cheap. But the advantages are massive, and the source really breaks them down into 3 buckets: material, speed, and quality.
Let's start with material. This seems kind of obvious. No runner waste. You save plastic. But is it really that much?
It can be huge. I mean, imagine you're making a tiny little part like a gear for a watch. In a cold runner mold, the runner structure can sometimes weigh more than the part itself.
Wow. So over half the plastic you're melting is just scrap.
Potentially, yes. Half your material cost is going, at least temporarily, into the trash bin. So if you're making millions of these, eliminating that waste saves tons of raw material, and you're not dealing with that regrind process.
Right.
Every time you remelt plastic, it loses some of its structural integrity. With a hot runner, you're always using virgin material, so you actually get a stronger, more consistent part.
That makes a lot of sense. So better parts and you save on material. What about speed? The source says cycle time drops significantly.
Yeah, and this is all about the physics of cooling. In a cold runner mold, your cycle is limited by the thickest piece of plastic in the shot, and that's almost always the runner.
So the part itself might be solid and ready to go, but you're just sitting there waiting for the garbage to freeze.
You are literally idling your million-dollar machine, waiting for the scrap to solidify. With a hot runner, you only have to wait for the part itself to cool. The runner is supposed to be hot.
So the mold opens, the part drops, the mold closes, you shoot again.
Instantly, it can cut seconds off the cycle. And in mass manufacturing, seconds are millions of dollars.
Okay, so it's cheaper on materials and it's faster. But the source also talks about quality. Things like weld lines and sink marks. How does keeping the plastic hot help with cosmetics?
It's all about consistency and pressure. Because the temperature is controlled right up to the gate, the plastic's viscosity, its thickness, is constant. In a cold runner, it's cooling down the whole way. It gets sluggish.
Sluggish plastic. I'm picturing trying to squeeze out cold honey versus hot honey.
That's a perfect visual, and that sluggishness causes defects. Sink marks are little dimples where the plastic shrinks unevenly. Weld lines are these visible scars where two flows of plastic meet but don't fuse perfectly because they were too cool.
But with a hot runner, the plastic flows like water, so it fills everything evenly and fuses perfectly.
Right, the pressure and heat stay uniform.
And what was that about valve gates allowing for absurd shapes? I highlighted that phrase from the source.
Yes, I loved that. Valve gates let you make things that would be impossible otherwise. Think about a huge, complex car dashboard.
Okay.
It's got curves, holes for gauges, thin spots, thick spots. You have to inject plastic at multiple points to fill it before it freezes.
But wouldn't those flows just crash into each other and create weak spots?
In a normal system, yes, they would. But with valve gates, you can sequence the injection. You can open gate 1, wait a second, then open gate 2, just as the plastic flow arrives there. You can literally steer the melt inside the mold.
That is wild. You're like conducting an orchestra of molten plastic.
You really are. It gives you this incredible mechanical control.
This all sounds perfect, maybe a little too perfect, and usually in these deep dives, this is the point where the other shoe drops.
Oh, the shoe definitely drops. There's always a catch.
I knew it. What are the headaches?
Well, the source is very clear on this. The first big one is thermal sensitivity.
This is about those specific plastics, right? Like PVC and POM.
Exactly. It comes down to what's called heat residence time. Some plastics just don't like to stay hot for a long time. PVC is a great example. If it sits in that hot manifold for too long, it degrades. It actually starts to release hydrochloric acid gas.
Wait, acid?
Yes, hydrochloric acid. It will literally dissolve the metal of the mold from the inside out. If your machine stops for a few minutes, you can essentially bake the plastic to death and destroy your system.
So you've got a corrosive bomb cooking inside your very expensive tool.
Pretty much. And then there's the color change nightmare.
Oh, I can just imagine. If you have this complex network of heated pipes full of, say, black plastic, and the next order is for white.
You are in for a very, very bad time. In a cold runner, you just shoot out the old color with the runner. It's self-cleaning. But in a hot runner, you have to purge all that black out of these intricate internal channels.
It sounds incredibly wasteful and time-consuming.
It is. It takes a long time and creates a ton of scrap. And maybe the biggest risk of all is leakage.
Right, the source mentioned that. What happens if it leaks?
It's the absolute worst-case scenario. This is molten plastic under thousands of psi of pressure. If a seal fails and that plastic leaks inside the manifold assembly, it fills up every space where the wires and heaters are.
So it basically encases all the electronics in solid plastic.
Solid plastic. Yeah. Imagine your car engine filling up with concrete. You can't just fix it. The whole system has to be sent back to be burned out in an industrial oven. It means catastrophic downtime.
And I'm guessing the initial cost is...
It's steep. Very steep. The tooling, the controller, the whole system is far more expensive than a cold runner mold. You're buying a precision thermal system, not just a block of steel.
Okay, that makes sense. I want to dig into that engineering side a bit more. The source talks about DFM, or design for manufacturability. This feels like where the real magic happens. What's the biggest hurdle?
In a word, thermal expansion. The source calls it the hidden killer.
Expand on that, pun intended.
So picture it. Your hot runner manifold is a block of steel, heated to, let's say, 250 degrees Celsius. Steel expands when it gets hot. It physically gets bigger.
Right, basic physics.
But the mold plates surrounding it are being cooled with water, so they might be at 40 degrees Celsius.
So you have a hot, expanding block inside a cold, rigid box.
Exactly.
Yeah.
And this system is designed for that. The manifold is actually made a little bit too small when it's cold. It only fits perfectly and creates a seal when it heats up and grows by a very specific, calculated amount.
That sounds incredibly hard to get right if you miscalculate.
If you're off by a fraction of a millimeter, you either get a massive leak or the expansion creates so much force it crushes the steel components. The design has to work perfectly across that whole temperature range.
Wow. And then there's the issue of balance. What's that about?
Flow balance. So, say you have a mold making 8 bottle caps at once. You need the plastic to arrive at all 8 of those cavities at the exact same time and with the exact same pressure.
Why is that so important?
Because if one channel is slightly longer or has a sharper bend, the pressure will be different. So one cap might be perfect while its neighbor is only half filled or has flash extra plastic squishing out.
So the layout of those channels has to be perfectly symmetrical.
Perfectly symmetrical. And on top of that, the temperature control needs to be incredibly granular. The source talks about multi-zone control. It's not just one thermostat for the whole thing.
Eating different zones?
You might have dozens of zones, separate controls for the manifold, for each individual nozzle, even for the tip of each gate. Because the edges of the system lose heat faster than the center.
So it's an active system constantly adjusting to maintain equilibrium.
It has to be. And here's a fascinating detail. You have to place the temperature sensors, the thermocouples, so they're measuring the temperature of the plastic, not just the steel around it.
Is there a big difference?
A huge difference. Steel conducts heat one way, but the plastic itself is an insulator. If you just measure the steel, you could be overheating and burning the plastic flowing through the middle without even knowing it.
You're flying blind.
You're flying blind.
So we have this incredibly complex, high-risk, expensive technology, but the source says it's used everywhere.
Oh yeah, it's the standard for the heavy hitters. Medical, for one. Think syringes, IV parts.
Why medical?
Cleanliness. When you break off a cold runner, it creates tiny plastic particles, dust. You can't have that in a sterile clean room. Hot runners produce a finished part with no secondary operations, no dust.
That makes perfect sense. Who else?
Automotive, big time. Dashboards, bumpers, lighting, and consumer electronics.
My phone case.
Your phone case, especially for thin wall parts. If you want something to be super thin but cosmetically perfect, you almost have to use a hot runner.
Why is that?
Because a thin cavity cools almost instantly. With a cold runner, the plastic would freeze before it could even fill the part. You need that hot runner to maintain pressure and heat right up to the last millisecond.
And packaging, I assume, is just a volume game?
Pure volume. If you're making 1 billion bottle caps, the material savings alone will pay for the system many times over.
So that brings us to the economic verdict. The source talks about TCO, total cost of ownership.
Right, the bottom line. And the argument is that even though the upfront cost is scary, for any kind of medium to high volume production, the hot runner almost always wins on TCO.
Because the savings on material and energy and cycle time just add up over the life of the tool.
Exactly. And the big one is automation. It's perfectly suited for lights-out manufacturing.
Where the factory runs itself.
A hot runner system just ejects finished parts. It can run 247 with no humans around. A cold runner often needs a robot or a person to handle the scrap.
So if you're making 10 prototypes, use a cold runner.
Absolutely. Keep it simple.
But if you're making 10 million, you have to go hot.
That's the rule of thumb, yeah. The break-even point comes when the savings outweigh that big initial check you had to write.
Okay, so let's just recap. We've gone from it's just a piece of plastic to this invisible molten vascular system running inside the machine.
It's a perfect example of trading simplicity for performance. A cold runner is simple, but it's slow and wasteful. The hot runner is complex and risky, but it's incredibly fast and precise.
It's like the difference between a bicycle and a jet engine.
And the consequences of failure are on another level, too.
Right. So what really stands out to you from this deep dive into James Lye's article? One key takeaway.
I think it's the interconnectedness of it all. The DFM section drove that home. The decision to use a hot runner isn't an add-on. It changes everything. The type of steel you use, the cooling design, the controller. It's not an accessory. It's the heart of the entire system.
And it demands a whole different level of human expertise. People who understand thermodynamics, not just mechanics.
Absolutely.
Yeah.
The source says you need highly experienced staff. You're basically managing a small thermal reactor. You can't just wing it.
So next time you pick up any plastic object, you can realize it didn't just get stamped out like a cookie.
No. It likely flowed through a precision-engineered, multi-zone heated manifold, balanced to a fraction of a second, expanding and contracting with immense force, all happening completely hidden inside a block of steel.
It definitely gives you a new appreciation for the mundane.
It really does.
All right, before we wrap, I want to leave everyone with one final thought. We talk a lot about automation, about the lights-out factory. But think about this hot runner system. It's a black box. It's sealed. You cannot see what is happening inside it. We are building these factories that run 24/7, and we are entirely dependent on the reliability of these invisible molten channels buried inside solid steel.
That is a provocative thought. We're implicitly trusting the physics to be perfect.
Exactly. And if the engineering inside that block fails, production stops. Globally sometimes. We're pushing for this invisible perfection, and it requires a level of trust in engineering that is, when you really think about it, kind of terrifying.
Makes you look at that phone case a little differently, doesn't it?
It sure does. Thanks for diving deep with us today.
My pleasure.
Keep looking closer at the world around you. You never know what you'll find inside. See you next time on The Deep Dive.